Barcelona, Spain, the Ministry of Universities, the Catalan government, and the Autonomous University of Barcelona have created a non-profit research institute called the Catalan Institute of Nanotechnology, which is associated with the Spanish National Research Council, forming a joint research center called the Research Center of Nanoscience and Nanotechnology, or CIN2. At the Institute, Dr. Daniel Maspoch and his team of researchers are working towards major developments in the science of the very small.
Basically, what I'm doing is like try to design, synthesize, and study novel molecular nanomaterials.
These microscopic materials and the techniques they're developing to build them have the potential to change the world around us.
Molecular nanoscience is a very powerful branch of science.
When you are doing your degree, you want to find something that is not in the book.
For me, this is like traveling to another planet.
One of the nanomaterials Daniel and Carlos are constructing is called a metal organic framework.
They are created from the linkage between an organic ligand and a metal ion.
These linkages form tiny crystals, and what makes them particularly useful are their hollow centers, which can hold a variety of payloads.
That has a wide range of potential applications, such as gas storage or drug delivery.
What we really want to do is to try to deposit a droplet and control the conditions in order that in each one of these droplets, this metal ion and the organic ligand reacts and it forms the crystal.
Because of their small scale, it's historically been difficult to control the materials and conditions required to build these metal organic frameworks.
It's hard to control the positioning of these precursors.
Recently, though, they have used a powerful technique called dip pen nanolithography, or DPN, to control the deposition of the basic seed material on a growing surface.
Dip pen nanolithography allows to control the miniaturization and positioning of these less than femtoliter droplets.
There is no other techniques almost that you can direct write liquids or nanodroplets on a surface at the nanometer scale.
Like a microscopic quill pen, DPN allows Carlos to load a tiny stylus with a solution containing metal ions and organic ligands.
So when you approach this AFM tip to the surface, it creates automatically a water meniscus that is used to transfer these molecules to the surface.
The process is considered a soft lithography technique, which means the printing should not affect the reactivity and functionality of the substances he deposits.
For me, it's the most powerful technique in order to direct write soft materials.
After printing, Carlos will need to wait a few days for the framework crystals to develop. We'll check back then to see if his work is a success. In another line of research, Daniel and Elena are working on a technique that will allow them to deposit a single molecule at a specific place, a fundamental ability that's never been possible before.
What I want really to do is to try to see if we can really print one single protein each time that we approach the AFM tip.
What we really want to control is the number of entities that you are delivering on each dot of the array.
With this ability, scientists could discover the interactions of substances on a unit level. For example, testing the interactions of single biomolecules.
You can study the interaction between the virus and the cell, or answer the question if a single virus can infect one cell.
To pursue this goal, Daniel and Elena use DPN to deposit very small volumes of a solution with a known concentration of an iron-containing protein called ferritin onto a delicate substrate.
And then, in principle, each time that you are depositing a droplet, you will deposit the number of proteins you have been calculated.
And I'm trying to get only one protein that is on this solution and put whatever I want on the substrate with nanoscale precision. So there are a lot of difficulties.
We'll catch up as Elena uses a transmission electron microscope to see how successful she has been. After giving his metal organic frameworks time to form, Carlos prepares to check his substrate for crystal growth.
We take the substrate, which contains these metal organic frameworks arrays, and then we bring to a scanning electron microscope.
Not only is he able to see the tiny spots where crystals have formed, he can also determine the shapes, sizes, and orientation of these crystals to better understand the way they assemble.
We can really control the reaction on each one of these droplets.
It's a significant success, one that has major potential to future technology. Let's see if Elena's work with single ferritin molecules is just as successful.
What we have to do is to get this substrate and go to the transmission electron microscopy.
And if you focus on each one of these spots, you can really count how many ferritins you are writing on each one of these spots.
She can clearly see the ring from the evaporated printing solution and also the individual ferritin molecules within each ring. The single molecules appear as tiny bright dots on her computer screen, but as this method is further developed for other materials, its significance will be far-reaching. The nanoscale materials and techniques that Daniel and his team are creating could lead to large-scale advances in the world around us.
With our results, other scientists can use this technique in order to improve their research.
We are not stopping it like doing fundamental research. We want to go one step further and see if we can really apply these molecular nanomaterials on the market.
It's going to be a great thing if I can see real technological applications.
As they move forward, they hope to see their findings used in industry and research that will impact our lives in incredible ways.
Now we have a lot of experience with DPN, so now we are able really to develop amazing things.